So we have 6.4 to tackle over the next few minutes. This is focused on the addition and subtraction of radicals. So first, in order to add and subtract radicals, we have to be able to understand exactly what is a like radical. Think of it similar to before you can add and subtract in algebra, you have like terms, okay? Well, we have like radicals. So two radical terms are considered like radicals if they have first the same index and second the same radicand. Okay, so if we have, by way of example here, an expression, right there, I just highlighted it in green, and I'm looking to see if these are like radicals. Sure enough, they have the same index of 4, and they have the same radicands, which is 5. So I can simply add their coefficients, 3 plus 4, times that like radical, the 4th root of 5. And so that's just going to give me 7 of those 4th root of 5s. Okay, so let me just take a second here and let's determine real quickly whether or not these few examples that I put on that I'm going to put on the whiteboard are like or unlike radicals. So if I have the square root of 2x, and then I also have the cube root of 2x, we ask ourselves, are these like radicals? Well, they need to have the same index. So we look, and for one of them, it's very clear, the one on the right, our index is 3. We have to recall that when we don't have an index, it's implied that it's a 2. So these are not the same indexes, and so they are unlike radicals. All right, let's look at another example. Let's say I've got the 4th root of x cubed, and then I've got the 4th root of 16x cubed. So we look and we see right away that the indexes are the same. The second criteria that we need to match is that we have to have the same radicand. So we look at these, and I look at x cubed, and then I look at the second one, and it's 16x cubed. So our initial feeling is, no, these are not like. Oh, but let's look a little bit closer. With that second radical, we could look at it as if it was we can take that 16, and that 16 is exactly the same as 2 to the 4th, x cubed. And so if I have an exponent that matches my index, I can simplify by bringing out the root. And so that then becomes 2 4th root of x cubed. Well, now my radicands are the same. And so these actually are like radicals. Okay, last one that I want us to look at. And this one is going to be, if I have negative 5 cube root of xy, and then I've got 4 cube root of xy. So 2 criteria to determine whether I have like radicals. First thing is I need to look and see whether or not the indexes are the same. They are. Then I look to see whether the radicand is the same. It is. So, but then I ask myself, yeah, but okay, I see all that, but the numbers in front, they're acting like coefficients. Those aren't the same. Doesn't matter. Okay? Just like if I had written this as negative 5x, I could even put 5xy and 4xy. If I asked if those were like terms, the ones written in the expressions written in pink, you would say, yeah, those are like terms because it doesn't matter if the coefficients are different. Same with radicals. These are like radicals. Okay? All right, so let's go ahead and do some examples where we add and subtract now that we're very clear as to what are like and unlike radicals. So first thing I want to look at with this first example is I want to look and see, are the radicals like radicals? So first, do they have the same index? So I'm going to look, so first index. And I'm going to say, yes, it's the same. Then I'm going to look at the radicand. And I'm going to say, yes, it's the same in both. They're both 6s. So because I meet both of the criteria, I can simply add those coefficients. So in front of the square root of 6, it's a 1. So I add 1 plus 2, and I get 3 root 6. I'm done. Okay, for subtraction, works just the same, okay? So I'll make this a little larger. So I can see here that I have like radicals because my index and my radicands are both the same. So now I just subtract 5 minus 6, and that gives me a negative 1 cube root of 3. Well, that's kind of an awkward way to write this. We don't put the 1. So I would really prefer if you wrote it as just negative cube root 3. There we go. All right, let's go ahead and look at C. So for C, okay, I look at my radical, square root of 2. My index is 2, my radicand is 2. I look at my second radical, exactly the same. So that means I just add my coefficients, 3/5 plus 2/5. Well, that's going to give me 5/5, which is 1. Well, I'm not going to put an implied 1. When I add these, I just get square root of 2. Because to put the 1 in front doesn't really do anything, okay? It's just an implied 1 in front. All right, let's look at D. So we have 3 terms here in this expression, and all 3 of them are like radicals, same index, same radicand. So now I can just subtract. I'm going to subtract 4 minus 2 minus 8. And so that's going to give me a negative 6. So I've got negative 6 square root 3. Okay, let's look at E. So for this one, I have 2 like radicals. The third one, square root of 2, is not the same radicand as the square root of 5. So I can only combine my first 2. So I add 7 plus 3, so I'm going to get 10 square roots of 5, and then minus 2 square roots of 2. That's all I can do with that one. All right, let's look at F. So for F, I've got all of the same radicals. So they're all like radicals. But we've got some addition, some subtraction. And then I just want to point out that this last term is not, not a like radical, obviously. All right, so we're going to go ahead and take 9 minus 4 plus 30. And so 9 minus 4 is 5, plus 30 is going to give us 35, and that's going to be the fourth root of 7. And then that minus 2 that doesn't have a radical attached to it, I just put the minus 2 on the end. Okay, I want to give you one to try. That's a little bit, well, actually, we're going to do some more challenging ones, and then I'm going to give you a one that's really fun to try. All right. Sometimes, just like this example, one of the examples I had with that 16 when we were looking at are they like or unlike radicals. Okay, sometimes we're going to have expressions that we need to simplify first before we go ahead and add and subtract them. Okay, so we've got this example that's in front of you that kind of is pre-made in terms of how to address it. Not my favorite way. I'm not a true fan of expansion. I just think it can create a lot of problems. It's easy to make an error. So let's rewrite this original problem here, and let's try it a slightly different way. So let's take 11 and the fourth root of x to the 7th minus 3x fourth root x cubed. Okay, let's start with that 11, okay, that first term. I'm going to, first thing I notice is that my exponent is larger than my index. So I want to use the multiplication property to rewrite the radicand. So I'm going to leave the 11, I'm going to leave the root 4, okay, the index of 4, and then I'm going to take that radicand and break it up. I'm going to take that 7 and count backwards until I get to a multiple of 4. So that'd be 7, 6, 5, 4, stop there. So I've got x to the 4th, and then I've got 3 x's left over because 7 minus 4 is 3. That helps us because now I have a exponent that equals the radical, and so I can take out 1x. So that is going to give me 11x fourth root x cubed. Okay, so I simplified that radical. Now let's go to our second term. Okay, so for this one, I have, my radical is already simplified. Actually, I'm going to just come down a bit here and just carry it down. So minus 3x fourth root x cubed. So now I have a like root or like radical. I'm sorry, let me pay attention to what I'm saying. I have a like radical and a like radical. But what you might not really pay attention to, and I want to draw your attention to it, is that the numbers and the variables in front are being multiplied by that radical. The variables have to be like variables, just like in algebra when we have like terms. So I need to have the same variable raised to the same power, which I do in this case. So because of that, I can subtract. If I didn't, if that was like one of them was an x squared, then I couldn't subtract them. Okay, but because they are the same, I can. And so 11 minus 3 is going to give us 8x fourth root of x cubed. There we go. And that's what we got up there using the expansion method. All right, let's jump into some more of these examples. All right, so with this first one here, it looks like I have unlike radicals, but that's just on the surface. I really need to dive in here a little deeper. So I have a cube root and a cube root as my indexes. So I am going to rewrite my radicans with those numbers underneath that radical sign. I want to look for anything that can be rewritten as a cube root. So I've got 5 cube root of 3, and I'm going to write 2 cubed x plus 5 cube root of 5 cubed x. Whoa, that's exactly what I needed. So right now I've got my exponents matching my index. So in both of those radicals, I can bring out a root. This is a beautiful thing. So now I have 5 times 2 cube root x plus 5 times the 5 I brought out cube root x. I'm almost done here. All I need to do is I need to multiply those coefficients. Okay, so that is going to leave me with 10 cube root x plus 25 cube root x. Because I have now like radicals, I can add 10 plus 25. I'm going to get 35 cube root x. Beautiful. Let's go ahead and look at another one, B. Okay, so first blush, looks like I do not have like radicals, but I really do think I can reduce here. Okay, so I can't do anything with the square root of 2a. So let's just leave it. Now I've got 4, but I can take that 72 and I can break that down. I'm going to break it down to, let me see right here, 36 times 2 times a. That's really helpful. We'll keep going. Now that 8a, I can break down to 4 times 2 times a. So in both those second two, I have factors that I'm multiplying that are perfect squares. And so I can bring them out. So I can't do anything with this square root of 2a yet. But with that 4, I can bring out the square root of 36 is 6. So my root is 6. And then I'm left with 2a. And then for this third term, that 4, the square root of 4 is 2. So I've got 4 times 2 square root of 2a. Okay, so now I've got square root of 2a minus 24 square root of 2a plus 8 square root of 2a. I'm in business. Only thing I need to remember that sometimes people forget is in this first term, there's an implied 1. So I'm just going to subtract, okay, 1 minus 24 plus 8, and then I'm going to attach square root of 2a. And so that is going to give me a negative 15, because 1 minus 24 is negative 23, plus 8 is going to give me a negative 15 square root of 2a. Beautiful. Let's look at another one. Here we go. So, same thing. We're going to start by simplifying each one of those radicals. So if you look at 150 and you're like, oh my gosh, I have no idea. You need to be thinking, what numbers are perfect squares, okay? So 4 is a perfect square, then 3 times 3 is 9, 16, 25. Oh, 25. Does 25 go into 150? It does. Okay, so if I think of this as 25 times 6, just think quarters, okay? You need 6 quarters to get to $1.50. X squared y. Then I've got plus 19. Okay, well, I can think of that 600 as 100 times 6, x squared y. Why is 100 beautiful? Because it's a perfect square. 10 times 10 gives me 100. All right, so I can bring out of this first radical, I can bring that 25 out. The square root of 25 is 5. So I've got 5 square root of 6x squared y. Then for the second one, this 100 I can bring out because the square root of 100 is 10. And then I'm left with 6x squared y. Wow. Okay, well, 19 times 10, that's 190, plus 5, I've got 195 square root of 6x squared y. Beautiful. All right, let's look at D. So for D, all right, I'm thinking, okay, with that, I wanted to go ahead, same process. So this is going to be 9 times. Oh, I'm thinking, what can I break 45 down into? What factors, what numbers can I multiply to get 45? And which one of them is a perfect square? 9 times 5. Okay, let's do the same thing with 125. Okay, how about if we go ahead and that's going to be 25 times 5. 25 is a perfect square. And then with 8, I've got, let me see, 2, 4. Does that work? We might be able to go higher. 16. 16 times 5 gets me to 80. And if that mental math is like driving you nuts, you could always do a prime factor tree, okay? And I could have done 2 times 40 gets me 80, 2 times 20, 2 times 10, 2 times 5, okay? Well, if you've got 1, 2, 3, 4 2s, okay, that is 16. The square root of 16 is going to be 4. All right, so let's go ahead and bring these roots out. So it'll be 9 times 3, because the square root of 9 is 3, square root of 5. So remember, 3 squared is 9. That's why I'm bringing a 3 out. Okay, for the next one, it'll be 9 times 5, square root of 5. Why did I do that? Because 5 squared gets me to that 25. There's that root of 5. Then I've got minus 8 times. The square root of 16 is 4, square root of 5. So now let's just go ahead, multiply those numbers out. 27 square root of 5 minus 45 square root of 5 minus 36 square root of 5. Add and subtract those coefficients. We're going to get negative 50 square root of 5. Oopsie. There you go. All right. Let's do another one. All right. Wow. This one looks crazy. Like, we haven't seen one with a plus sign in the middle. Huh. I'm going to give you a second to look at it. So, if we look at this radicand, the first obvious thing we notice is that there's a 49 in both terms. So, what we can do here is we can factor, okay? So if you factor out a 49, then you're left with x plus 1, okay? And out of the second radical, if we factor out an x squared, you're left with x plus 1, okay? So 49 is the same as 7 squared. So that means we could bring out a root of 7, and then underneath that radical, we're left with that x plus 1. Then out of the second one, the square root of x squared is x, and we're left with x plus 1. Ah, such a lovely thing. So now I have like radicals, so I can add them. But it's important that you show your answer correctly. If I wrote 7 plus x, and then I wrote square root of x plus 1, that's wrong, okay? Because it just looks like the x is being multiplied times that radical, and that's not what you intended. You need to put parentheses around that expression, 7 plus x, to show that that's what you intended. It's that quantity, 7 plus x, that gets multiplied by that radical. Fabulous. Okay, let's look at f. Wow, we got fractions in here. It's okay. It's all right. Not a big deal. Okay, so it doesn't look like anything matches up. However, remember how I showed you you can separate a fraction into the top and the bottom, okay? And so let's do that. Let's take the 4th root of y cubed over the 4th root of 81, okay? Minus 5 times the 4th root of y cubed over 3. Well, 81 is equal to 3 to the 4th. So I could substitute that 81 with 3 to the 4th. Okay? Our exponent matches our index. So I can pull out that root. That base of 3 becomes my root. Okay? And so I have the 4th root of y cubed over 3 minus 5 times the 4th root of y cubed over 3. Well, there's a couple things to note here. One, I have like radicals. Beautiful. I also have denominators that are the same. So I can subtract those fractions. That's easy. I've got my denominator of 3, and then my numerator is 1 minus 5, gives us a negative 4, and then my radical would be the 4th root of y cubed. This is my answer. Beautiful. All right. Let me have you real quickly try something. Okay, right here. So pause, try that problem, and then press play. All right, so as we're coming back here, first thing I want you to do when you're looking at this problem is I want you to convert that fractional exponent to a radical. So remember, it's exponent in the numerator, index in the denominator. So I'm going to put the 3 in the index, and my 4 is going to be my exponent. And so I am going to write this as xy to the 4th. Okay? And now I'm going to let me keep going with this one. Okay? I'm going to keep working down here. So I see that my exponent is larger than my index. So I'm going to work my base here, or rework my base. So I have two factors or two quantities in parentheses that are being multiplied. And so that's going to be, there's my cube root. So I'm going to do xy to the third, xy to the first. So my base is xy, so I have a like base. And if I add 3 plus 1, it gets me back to that 4. Why do I want to do that? It's a beautiful thing. My exponent and my index match. So now I've got on the outside my root of xy. Then I've got my cube root and I have an x1 underneath. Okay? Let's go to my second term. So I've got here this 4 with my is only attached to the y. It's not attached to the x. And it's larger than my index. So I am going to rewrite this so that it's 2x cube root of x, y cubed, y. So now I've got this y that has an exponent of 3 that matches. So I can bring out that y. The root of that is going to be y. So I've got, I'm going to go down here. I'm going to do plus 2x. That's part of my 2x down here. I'm going to bring out my y, and then I'm left with the cube root of xy. Oh my gosh, look at that. I have like radicals. And also what I have is my variables are also like. So I can just add. So this is going to give me, I'm going to have 3 of these because there's really a 1 in front there. So 3xy cube root xy. Wow. I'm pretty sure there's a problem like this on the homework. All right. Now, let's very quickly go back and do this problem number 2, which is a perimeter problem. So perimeter is just the distance around an object. So the distance around. Okay. So I know because this is a rectangle, the opposite sides are the same. So I've got an x and a square root of 20 and a square root of 20. So I could say perimeter is x plus square root of 20 plus square root of 20. Absolutely. And then you combine your like terms and you've got 2x plus 2 of those square roots of 20. That's your perimeter, which they gave you as 24 root 5. Now, most people would start right there at that line. Because when you're thinking about perimeter, you always think of it as being 2 of the widths plus 2 of the lengths. And x can represent your width and root 20 can represent your length. If you put those in opposite order, it doesn't matter. All right. And so next, I'm just going to go ahead and solve for x. So to solve this problem, the first thing that I want to do is I'm going to subtract 2 root 20 from both sides. And so that leaves me with 24 root 5 minus, now I'm going to start simplifying a little bit. That 20 can be thought of as 4 times 5. Okay? And all of that's equal to 2x. But I can bring the square root of 4 out. So I've got 24 root 5 minus 2 times 2 root 5 equals 2x. Well, 2 times 2, let's just make an adjustment here. That's just 4. So now I've got 20 root 5 equals 2x. Divide both sides by 2, and I end up with 10 root 5 is equal to x. That's what our x is, 10 root 5. This is what we refer to as an exact answer. If you try and put it in your calculator and round, now you've introduced error, but just a little bit of error into your answer. So unless it's asking you to round, and how do you know if it's asking you to round? If it's asking you to, it'll tell you round to the hundredths place, round to the tenths place, okay? Something like that. If it doesn't ask you to round to a certain place value, then give the exact answer. All right, let's do this next one. So for this one, they're giving us a perimeter of 10 root 2, find the value of x. Okay, so it's really very much the same. It's going to be, so our perimeter is 2 widths plus 2 lengths. So 10 root 2 is equal to 2. I'm just going to do root 8 plus, I'll call my length x. Okay, so now I'm just going to go ahead and subtract 2 root 8 from both sides. So 10 root 2 minus 2 root 8 equals 2x. I could simplify life a little bit right now by just dividing everything by 2. That's a little bit of a deviation. Let me do it exactly how if you choose to do that, that's okay. But I'm going to go ahead and simplify 2 root 8. So 10 root 2 minus 2, 4 times 2 equals 2x. I'm going to bring out a 2. So I end up with 10 root 2 minus 2 times 2 root 2 equals 2x. Let's just divide everything by 2. Okay, so now once I simplify, 2 goes into 10 5 times, and then one set of those 2's reduce. So I've got 5 minus 2, which is going to be 3 root 2. That's what x is equal to. Okay, all right, so you were fabulous. Okay, I can feel it. I can feel that you understand everything. So now you're ready for your homework. Go to it.